All right, let's start. Hola a todos. Welcome to this performance tips and trick from a Unity consultant talk. My name is Nicolas Borromeo. I'm a senior software development consultant here at Unity. And my job consists mostly on reviewing client projects, assessing their performance, and help them optimizing their projects. So that's a little bit of the reason I'm here right now is because as a Unity consultant, we see Unity in a wide variety of contexts. We see it being used in mobile applications, console games, desktop applications, VR applications. We see Unity being used for industry, for gaming, and for a wide range of genres, like from simple mobile games to full city building simulations. So in this experience, as consultants, we tend to see lots of performance issues repeat in all of these projects. And the idea of this session is to share some of the tips and tricks we learned during this job. So in this session, we are going to discuss first a little bit of advanced profiling. From the previous performance session, you might have you saw all the Unity profilers, but we will go a little bit deeper into other ways to analyze performance with other profilers. Then we are going to discuss a little bit about the most common CPU performance issues, the most common GPU performance issues, and finally, the most common performance issues regarding memory, essentially how to prevent your application from crash due to out-of-memory issues. So let's start first talking about profiling. When talking about profiling, sometimes you think that profiling is only a matter of profiling, the gameplay loop, so how physics are doing, how rendering is doing, and so on. And while that's perfectly true, there's way more areas which we can use the profiler to get performance. So as an example, we can split the different hotspots between maybe player performance and editor performance. So you can first analyze the performance of your build, your executable, your APK, and so on. And from there, you can analyze, of course, as we mentioned before, gameplay loop. So again, rendering physics, your scripts, and so on. But also, you can analyze loading times, how much time you're spending loading assets, or maybe how much time you're spending doing server calls and waiting for the response, instantiation times. Also, you can analyze spikes, of course. These sudden frames that take longer than expected. Again, can be instantiation, activating and deactivating objects, sometimes expensive, and so on. But you can also use the profiler to analyze the editor. You can analyze, as an example, asset importing times, how much time we are taking to import textures and why. Maybe you are executing custom post-processors that are taking longer than expected, or maybe some plugin includes custom post-processors. You might be wondering about scripting, how much time you are spending compiling your scripts, which assembly is taking longer, and maybe some dependencies are causing issues. You might be also wondering why the domain reload takes so much. You can use the profiler also for that. And also building times. You might want to analyze why your application is taking so much to build, why Addressables is taking so much, why scene building is taking lots of time, and of course, custom building steps that you might be using. So you can profile a wide array of things with the Unity profiler. Now, when you use the Unity CPU profiler, it's a great tool. And just to let you know, it works under the principle of instrumentation. That means that in specific performance hotspots in the Unity source code, we added markers to analyze performance. As an example, here we can see late behavior update is a marker we added that calculates the time it takes to execute your script's late update. So it's a great tool, but sometimes you need more information. In this case, as an example, we can see that water.lateUpdate is taking 1.5 milliseconds. That's great. We know that that script's an issue. But now we can open the script, we can start to figuring out what could be, and we can do better than that. So you might be thinking, OK, we can use the tip profiler, which is, of course, a great solution. You can see the full call stack of every single C# function that was called in your application. But the timings are completely irrelevant. You just don't trust the timings in the tip profiler because the act of profiling, analyzing the performance of every single function call is more heavy even than sometimes the function itself. So, and also, it only shows you C# functions. So if you want to see what, as an example, you might be calling an API that is doing something in the native side, you have no clue with this profiler. So sometimes you need even more information. And here is where native profilers kick in. This is a pivotal tool in my job as a consultant, because you have profilers, native profilers that are per platform. So you have profilers that are specifically dedicated for iOS, for Android, for PC, for consoles, and so on. As an example, in iOS, the biggest one is instruments. So these tools, at least the CPU profilers, works under the principle of sampling profiling. You will measure the performance of your game during, I don't know, 10 seconds or so, and these profilers will sample the entire native call stack, every single function that were called at a given frequency during those 10 seconds. So it will tell you which function was mostly called during your recording time. So in this case, you can see how we get plenty of information from a simple act like activating a game object. We can see that most of the time taken by activating the specific object was due to calling the native side awake method of the mesh collider. We can tell that it's native because of the classic C++ characteristic : syntax. So if we keep exploring, we can see that actually the cost of awakening this mesh collider was due to cooking the physics mesh. Essentially, you need to convert the render mesh into a physics compatible mesh. That specific problem is outside the scope of this presentation, but I wanted to show you how much details you can get from these tools. And the thing you need to consider is that these tools, given they are native, they usually only work when your player is built with IL2CPP, because usually they don't recognize mono call stacks. But consider that there are some tools that actually recognize mono call stacks. As an example, Superluminal, which is great because, as an example, in the editor, you don't have IL2CPP. IL2CPP is only happening on builds. So if you want to learn a little bit more about how to use Superluminal, I recommend the Unity Learn article, Profile CPU Performance with Superluminal, which tells you the workflows to use this tool. But actually, let me show you an example of how to use it. So I open Superluminal. It's a Windows-only tool. I'm just running Parallels on Mac, but you need to use it on Windows. And I will open a capture I did. In this case, it's a capture from a client who was wondering why Addressables was taking 10 minutes to build. So we put Superluminal, put any Unity to build, and then start recording. You can see that we have a recording of 10 minutes. And you can see things like, as an example, I don't know, all the threads that were running during this time. And also, you can start analyzing all the methods, all the call stacks that were called during that time. In this case, I want to focus on Addressables content building, so I will look for the method that kicks all that process, with this called build player content. You can find it right here, Addressables asset settings.build player content. So essentially, I just found the method. And if we switch to timing, you can see that it takes about 10 minutes, which is, what we expect. So from now on, I want to focus on this branch. I can double-click or right-click and set as root to focus on that. And I can switch the time display to absolute to essentially see how the methods called by this method compares to the overall time of building Addressables. So now we can start going deeper, 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 and see all the methods. This is actually C# methods and C++ methods that are called. And we can start analyzing how, as we start exploring, how the timings start to split between the children. And as an example, in this example, we reach this case where we get to the point where we execute the method that run all the steps involved on Addressables building. And we can see that 86% of the entire building process is spent on Atlas cache regeneration. So that's great. Now we have something to focus, sprite atlases. But we can do better. We can keep exploring and start saying, OK, what packing atlases involves? And if we go, eventually we can find this other case. Like 49% of the time is spent on compressing textures. You might have unoptimal compression settings or sizes. And again, we can keep going and going. And in this case, we get to the point where we can see that we are actually using ETC compression. So now you can think, OK, we might be using ASTC instead, or making smaller textures. Now the conversation can go to other places. But my point here is that you can see very, very detailed information about what exactly Unity is doing and your build as well. So that's about profiling. Now let's discuss a little bit about the most common CPU performance issues. So shader compilation spikes is one of the most common ones I see. Just to recap, remember that your shaders have variants. So every shader has different versions of the shaders with different combinations of features. So if you have a material that, as an example, is using the lit shader, and you didn't set the normal map as an example, you will be using one of the many versions of your shader that doesn't have the normal mapping code. So I imagine that in complex shaders that consider different APIs, BR, not BR, and so on, you can have hundreds or even thousands of shader variants. It can scale really, really fast. So every single one of the variants that you use for the first time needs to be compiled. Even if it's the same shader, you might be compiling different shader variants. So essentially, you will see that this time is shown in the profiler under the shader create GPU program marker that is usually on the render thread. This essentially means the time that is consumed by Unity in order to send the shader variant data to the GPU driver and let the GPU driver do its thing. So what you can do to prevent this, because this can happen during gameplay, and you can start experiencing hiccups during gameplay, and especially in VR, that's something that can be pretty annoying. So here's where shader pre-warming kicks in. The idea is that you will compile the shaders before the gameplay starts. You can first detect which are the shaders that you're actually using, not the millions, or, well, thousands of variants you might have. So one way to determine which shaders you actually need is using the log shader compilation flag in the graphical settings. This will essentially mean that if you make a build with this setting, you run the game and close the game, you will find a log that will contain all the shader variants that you compile. So you can play the game, execute it as thoroughly as you can to trigger as many scenarios as you can, and then use that to create a shader variant collection, or an SVC. It's an asset that will contain a list of shader variants. You can automatize this process using the project auditor. This is a Unity package that you need to install separately, which do a lot of stuff regarding analyzing your project. But one of the things it does is taking this log and converting it to a shader variant collection. Once you have this asset, whenever you want to pre-warm your shaders, you can call the warm-up method in the shader variant collection. But shader variant collection has some things that you need to consider. First, or actually the biggest one, it doesn't work well with modern APIs, Vulkan, DirectX 12, and so on. Because these APIs have, let's call them sub-variants of your shader. So even the same shader variant can be compiled into different shaders depending on the GPU state. So if you have meshes with different vertex attributes, in these newer APIs, you will have different sub-variants, let's call them. So the most reliable way to pre-warm shaders in these APIs, as of now, as of Unity 2022 and before, is essentially rendering your some mesh that uses the same vertex attribute format using the exact same URP assets and all the pipeline state that you use normally in your game, but behind a loading screen. So it's kind of a manual work, but should work. But in Unity 6, we have solved this. We have now the concept of PSO caching, or pipeline state object caching. It's a very similar API to shader variant collection. You can essentially create a graphic state collection, record all the shaders that you compile during a given playtime session, and then store this to the pre-warm this graphics variant collection with, again, the same API of shader variant collection, or a very similar one. I recommend you to check the Unity discussions thread called Graphics State Collection Tracing and Warm Up. You can get more information about how this works. Now, other common thing that we see is essentially a misuse of batching. Just to keep everybody on the same page, remember that batching consists essentially of grouping elements that share the same GPU state. So whenever you want to render something, you need to set up the GPU to use specific shaders, specific textures, specific uniform buffers or vertex buffers, and so on. So whenever you need to change the GPU state to represent any other material, that's expensive. That's why we try to group elements that have the same shader state and change the GPU state and render all the elements that use the same GPU state. And you need to have plenty of ways to do this. We have the static and the dynamic batchers. We have the SRP batcher. You have instancing. And you can even use low-level APIs like draw mesh instance. So I won't go through detailed explanations on how each one of these options works, but I wanted to give you some tips. Please, the first thing I would recommend you to do is to not skip on the SRP batcher. If you are using any SRP like UURP or HDRP, you can use the SRP batcher, which is a way more flexible tool compared to, as an example, dynamic batching. It can batch elements that uses different materials as long as the materials uses the same shader variant. And also, essentially, you can batch elements with less restrictive vertex limits compared to dynamic batcher. You need to be sure that your shader is compatible with SRP batcher. You can check in the inspector when you select a shader if it's SRP batcher compatible with that little property right there. And you have information in the documentation about what you need to do to make your shaders compatible. Usually it's a simple change regarding some C buffers. Also, you don't need to use material property blocks. Those are intended to be used alongside instancing, and essentially instancing and SRP batcher doesn't play well together. It's one or the other. So if you are using material property blocks, we are not going to execute SRP batcher for those objects. So it's perfectly fine to have thousands of materials with different colors if you want, as long as they use the same shader variant. Talking about instancing, sometimes instancing can be better than the SRP batcher. It's a little bit of a project-dependent thing, but usually, as a rule of thumb, you can think that if you need to render the same mesh more than 100 times, usually GPU instancing is a better solution. So try to use both in the best way possible. Finally, you have low-level APIs like the draw instance APIs or the batch render group, which allows you to render objects without the overhead of having game objects, renderers, transformations, and so on. So it's a little bit low-level, but it's a very powerful tool. So actually, let me show you how render mesh instance can improve your performance. So in this demo, I have this kind of sea with things around, like cubes going around, spheres, and so on. I'm using this for a game where I want to just have some nice graphics. This is not gameplay related. This is just some voids that move around and do nothing. And if we check the frame debugger, we can see that all of them were rendered in just 4 draw calls. 1 for the cubes that are flying on top, then 2 for lots of cubes below the sea, that you can see that they are around 500 instances, 200 instances, 300 instances, and then the spheres, another set of 300 instances. So essentially, 1,200 elements being rendered in just 4 draw calls. And no, I don't have 1,200 game objects to load, to parse, to spend time loading them. This is because these game objects use a custom script IDE that executes the low-level APIs. So in this case, I won't go into the details of how this works, but at least some things to notice is that I have a native array of matrices, which represents the position, rotation, and scale of the objects. Then in the update, I'm using jobs and bursts to update those to represent the logic of how the voids will move, how they follow a leader, and so on. But the part I wanted to show you is that later, in the late update, when those jobs finished, I execute rendered mesh instance to say I want to render that mesh as many times as void matrices elements have in the positions specified by there. So it's just a single line of code, and I have a lot of elements on screen. Also, another common issue we see is multiple cameras. Especially since URP, each camera has severe overhead. You need to execute cooling and maybe occlusion cooling if you have some enabled. You will need to create the render graph if you are using the newer version of URP or HDRP. You need to prepare render passes and so on. You can see in the image how we have certain markers, and in the submit marker, which is the marker that is actually issuing draw calls to the render thread, you can see that all things that comes before are actually just preparation for start issuing draw calls. You can see that actually the overhead of preparing the camera is bigger than the rendering itself. So this multiplies as more cameras you have. So essentially, avoid having multiple cameras, reduce your camera count as much as possible. If you need to render elements on top of the existing camera results, you can use render features as an example to create custom maps for custom post-processing effects. You can even do some tricks like rendering elements that are being seen in the camera into a separate render texture to use in UI or something like that. And another case is like avoid separating the UI and the 3D camera if possible. Sometimes I see cases where clients use camera space UI canvases to render 3D elements in the middle, but to avoid the camera from overlapping the 3D world, they just choose separate cameras. Well, that makes perfect sense. If you want to really avoid the second camera overhead, you can just use clever tricks to prevent the UI from colliding with the 3D world. And if you really need to use multiple cameras, consider that you, as an example, in URP, you can set in your URP asset multiple universal renderers. So you can have different universal renderers with different settings. And you can create one for the 3D world and one for the UI. Because, as an example, in the UI one, you won't want ambient occlusion, as an example. So at least you will reduce a little bit the cost of the extra camera. Finally, regarding CPU improvements, I want to talk about some of the ones upcoming in Unity 6. One that you probably already heard of is the resident drawer. Essentially, it is an implementation of the batch renderer group, but for game objects. That API was created for dots, and now it's being used on game objects. One of the many things it does is to essentially do a very efficient instance-based batching. So it also includes GPU occlusion cooling, as we already mentioned several times. But another interesting feature, a little bit of a low-level one, is split jobs. It's something that is available in DirectX 12 in Unity 6. Essentially, it's a new multi-threaded rendering model for rendering. So remember that rendering happens in multiple threads, especially if you use graphic shops. This is a new mode that will reduce a lot the synchronization time between the threads. And again, it's available in DirectX 12. Again, Unity Discussions has a nice thread about this, DirectX 12 and graphics shops improvements. OK, now let's discuss a little bit about GPU performance. So the first thing you want to know about GPU is that if you really need to worry about GPU. So you need to know if you are GPU bound. Usually, the most reliable way to detect this is through, again, native profilers. They will provide more accurate timings. But you can infer if you are GPU bound checking certain profiler markers. The truth is that this is a little bit difficult sometimes because different platforms have different markers called differently, like Vulkan or even in Quest 2 that has its own graphics compositor. Some things are managed in the graphics compositor side, and they are not very clear in the Unity profiler. But usually it looks something like the main thread waiting for something happening in the render thread, usually in the form of wait for present on GFX thread marker. And then you need to check what is actually doing the render thread, because it might only be waiting for vertical sync or the target FPS. But if you see something like present frame, unless you have a compositor that might be doing vertical sync on its own side, usually this means that the render thread is waiting for the GPU to finish. So try to look at these patterns in your profiler capture to see if you are GPU bound. If you are GPU bound, some of the most common issues I see in those cases is overdraw. Overdraw consists of repeated rendering of the same pixel over and over and over again. And it's especially an issue in UI and any kind of 2D rendering because this uses transparent rendering techniques. This usually involves rendering elements back to front in order to achieve proper transparency. And of course, we need to disable the CDEP tests for this to work properly. So as an example, if you have a UI being occluded by another UI completely, like an options menu hiding the main menu, you will want to disable the main menu. Or another case is that you might have an element hidden through alpha. That means that the elements won't be visible, but sometimes, depending on your configuration, you might still sending this completely transparent object to the GPU, and it might be rendering and wasting performance without you noticing it. So we recommend using, again, native GPU profilers, RenderDoc, Pix, NVIDIA Insight, or any of the platform-specific ones. So let me show you how to detect this in RenderDoc. So I won't go through all the details that it took in order to take this capture, but we have plenty of guides about that. But the point here is that the only thing I see regarding this rendering is just a white square. So I literally have a white square using UI in my game. So just by looking at this, I say, OK, everything is good. But if I switch to some of the visualization modes, like quad overdraw, you can see that something weird is happening. So we have a white rectangle, but we have this kind of heat map showing us that there's something else being rendered. So in this sense, we can go back to normal rendering. In this sense, RenderDoc works pretty similarly to the frame debugger. It can see individual draw calls. Instead of batches, you will see individual draw calls. And you can see that before rendering the white square, I'm rendering some text. And after rendering the white square, I also have some invisible thing. It's like, what is doing this? You can switch, as an example, to the highlight draw call view on RenderDoc to see the draw call that this is doing. And you can see that we are actually rendering pixels, but no results at all. So here we can start researching if we want. We can go, as an example, to the mesh viewer to see that we are actually rendering one quad. But then we can see that the colors are red in the case of the quads, but alpha 0. So in this case, we are rendering something that is completely transparent with no reason at all. This is wasting performance, and it wastes quite a lot, especially if you are using expensive shaders. So we recommend, when you are GPU bound, to take a quick look at overdraw to see what you can do about it. Another form of overdraw, which is a little bit less known, is quad overdraw. Quad overdraw happens when you render small pixels. For example, I mean, all GPU pixel operations usually works in quads or in small 2x2 pixels arrays. So even if you have a single pixel triangle, you are actually rendering 4 pixels to calculate derivatives and so on. So you might have a very, very dense mesh being seen very, very little, and you might have lots of little triangles, 1-pixel triangles overlapping. You might be rendering a lot of times the same pixels over and over and over again. So here, the classic vertex density reduction techniques apply, like using LOD or HLOD. So you don't only reduce the vertex shading costs, but most importantly, you reduce the pixel shading cost. Nowadays, modern GPUs are more worried about pixels than shaders, especially with 4K resolutions and that kind of things. So pay attention to your little triangles. And actually, this is a visualization that comes with HDRP in order to detect this on the editor. Finally, regarding GPU, I want to talk about shader performance. Again, you might have issues in the GPU side, but it might just be that a single draw call is taking a lot of time. As we saw in RenderDoc, you can see draw calls. In other tools, you can actually see the timings of those draw calls. And you find that a draw call might be rendering just a bunch of pixels, but still is very expensive. You might be having issues in your shader. So there are plenty of shader profiler tools. As an example, in the image, we can see the NVIDIA Nsight shader profiler, which can point you to the exact methods that are actually taking lots of time. Profiling shaders is not easy. It's a very complex science. You need to learn a lot of how the GPU works. But at least I want to let you know that this exists. So again, there's lots of things that can happen here, but the most common things that you might be looking for is, as an example, reducing the ALU operation costs through replacing floats or ints with half or int16 types if your graphic card supports them, because these essentially are cheaper operations, so half precision, but you might not need full precision. I don't know, if you are representing normals or something like that, usually half is enough. But also, they use less memory. And this means that each pixel needs less memory to be represented in the GPU, which means that you can fit more pixels in the same warp, as NVIDIA called them. So essentially, you can process more pixels in parallel. In the same line, try to reduce your variables. So this can translate as registers. So the more variables you use, the more registers you will use. Hence, less pixels will fit in a single warp. So of course, the compilers do a nice work in reusing variables for you, but sometimes they need your help in order to prevent some scenarios. Also, something that seems weird, but avoid using ifs. Like the regular if is very, very bad for the GPU due to lots of reasons. But the main point is avoid using them. Instead, use static batching or shader keywords. So essentially, you will be creating a new variant or set of variants of your shader, but having your code enabled or disabled. So essentially, we are making variants through special ifs that uses keywords. And finally, reduce texture or any kind of main memory access like dynamic buffers access. So essentially, everything that might require going to the main memory to read some data, like textures, it's very expensive. You have caching mechanisms, but still you need to pay the price sometimes to go into main memory. So you can do classic tricks like combining 4 single-channel textures in 4-channel textures in order to retrieve 4 values in one texture fetch. Or if you are using buffers, try to use constant buffer instead of the other ones. So well, that's regarding CPU. Now I want to finish with memory performance issues. And one of the most common and most hideous problems is untracked memory. This is usually huge. And untracked memory is essentially any kind of memory that your allocation allocated that didn't went through the Unity native allocators. So essentially, Unity has native allocators of different flavors for different purposes. But sometimes certain plugins, or maybe your own plugins or native code, might be allocating memory not using them. We provide an API for plugins to use the Unity native allocators in order for them to be recognized by the memory profiler. But not every plugin does that. So usually it's just plugin allocations. And the first thing to notice regarding untracked memory is that most of the times it is just non-resident memory. Remember that your application, if you want, can allocate 50 gigabytes of memory, but you might be only using 200. Those 200 are the ones that matter, the ones that might cause out-of-memory crashes. So since Unity 2022.2, the memory profiler can differentiate between allocated size and resident size. In this case, in this image, we can see how the memory profiler reports 0.75 gigabytes of untracked memory. But from those, actually, we are only using 140 megabytes that are present in your physical RAM. And in some cases, in some specific devices like iOS, some of that memory might be swappable. Again, you can use the memory usage on device documentation of the memory profiler, which clarifies a little bit more these concepts. But if you're in older Unity versions, this differentiation doesn't exist. And again, native profiler comes to save the day. So in this image, you can see how we start to cross-reference the information that the memory profiler gives with native profilers. In this case, I'm using instruments. So in the image, you can see how we enable the memory map feature of the memory profiler. This is something that you need to enable in the Unity preferences, not the project preferences, the Unity preferences, to allow the memory profiler to show this new tab. And this is a detailed breakdown of all the allocations that are present in your memory capture. So you can see that you can see the individual untracked allocations, some label that the operative system gives. Like, for example, malloc small is an iOS-specific label. And the address. So you can start cross-referencing, OK, this 8 megabytes memory, what it means. So you can use as an example the instruments VM tracker profiler, which allows you to essentially take a snapshot of your memory, and you can essentially look for that address, and you get more detailed information, like the virtual size or the full allocation size, and how much of that memory is actually resident on physical. So in this case, we can see that we have a 100 megabytes allocation, but only half of it is occupying physical memory. And also, you will see some concepts like dirty or subsize, which are kind of iOS specific, so I won't go into details about them. But I recommend you to see the WWDC 2018 video called iOS Memory Deep Dive. It's an Apple video that will go into details of how the iOS memory architecture works. It's pretty informative. So and again, you can start cross-referencing to get that resident versus allocated memory using native profilers. And you can go even deeper. As an example, the instruments allocations list tool allows you also to, again, cross-reference the addresses and then look to which method actually created this allocation. And with a right panel that I'm not showing you right now, you can actually see the entire call stack to see who allocated this memory. This example, we are seeing lots of AK platform allocations, which is usually related to WISE. And you can follow the call stack to see which of your C# methods might have allocated this, or which thread, if you want. So it's a little bit of a very, very deep work, but can clarify a lot about your untracked memory. Then another classic we see is the reserve managed memory. Essentially, is memory that is allocated in C# that you have allocated, but you are not using. This will never be untracked memory, because untracked memory only happens for native allocations. So for understanding this one, I would like to discuss a little bit about how we allocate, or how our implementation of the Bohem GC allocator algorithm works. So essentially, C# allocates memory in this kind of sections, like 1, 2, 3, 4 megabyte sections. The size changes over time. So all these different chunks of memory that are scattered through your RAM is what we call the managed heap. Whenever we need to allocate an object, we take one of these sections and we split it between, you want to allocate a 200 kilobyte objects, we will split it between 200 kilobyte section and the rest of the empty memory, in a way that then other allocations can use this empty memory. As these allocations are released, the contiguous blocks that are free are going to be merged to have a nice contiguous set of memory. And this is where the first issue happens. If you don't release this memory, you cannot merge the object contiguously. So if you want to fit a larger object in these sections, it's completely fragmented and you cannot fit it. But this is even worse for small allocations, which actually is the most common ones. Because this division of the sections happen at a 4 kilobyte granularity level usually, meaning that the smallest block you can get is 4 kilobytes. So if you want to allocate usually larger than 2 kilobyte allocations, we take the entire block, we fit the 2 kilobyte or plus allocation, and leave the rest just to be empty. But for smaller allocations, which again are the most common ones, we don't waste a lot of space. We instead take a 4 kilobyte chunk, split it into buckets, and start allocating different object sizes inside it. So smaller allocations go into a single 4 kilobytes block. And again, the issue happens again, as if you don't release all the objects in these 4 kilobyte sections, essentially you will be holding the entire block and preventing it from being merged with the rest of the blocks. So again, this happens a lot, and this is the most common issue. And you can detect the actual size of reserve memory in the memory profiler. If you go to the all of memory tab, manage reserve section, you can see how much memory you are wasting or pre-allocating for these options. So in this case, 28 megabytes is not the end of the world, but I have seen worse. Nice, we know how it works, what we can do about it. So actually, I already talked about this. So essentially, avoid allocating long-term memory along temporary memory, because you might be allocating lots of small objects in a block, splitting the block into little chunks. And then one of those objects might be long-term, and the other were temporary, I don't know, some list you allocated to filter another list, and then throw away the list. And you might end up having a 4 kilobyte block occupied by maybe a 10 bytes long-term object. So if you instead try to initialize, as an example, instead of lazily initializing long-term managers, you initialize them, all of them at the same time without allocating any temporary memory in the middle, you might end up having lots of the long-term objects living in the same blocks, preventing from the fragmentation to happen. Also, you need to avoid allocating memory every frame. You can check in the memory profiler how much memory you are allocating every frame, because usually this is probably temporary memory that will be, making your sections to not be properly utilized. And we have a feature called the call stacks feature that allows you to see the entire call stack whenever you do a GC alloc. Actually, I will show that in a moment. But if you want to go even deeper than that and go to the guts of your memory, you can again use the memory map feature I mentioned before. And in it, you can actually find managed heap sections, these 4 kilobytes or larger sections I mentioned before. In this example, we can see a 16 kilobyte section only occupied by the array of floats of 32 bytes. So it's quite the waste. Consider that for this view, we might not have the entire information, so it's kind of an approximate of the entire thing, but should be pretty reliable. Another recommendation is try to use to avoid allocating temporary memory in the managed memory. Sometimes you can instead use native collections, like the ones that usually are used in dots, but you can use them in regular C# objects, because those go through native allocators that have specialized allocators for small, long-lived objects. So sometimes, if you can do it, use them instead, might be better in terms of performance. So let me show you the GC call stack feature. So in this case, I have this profiler capture. I take the capture having this call stacks option turned off. So you need to pre-enable this before recording. And then you can start finding for the UC alloc markers, which is usually these purple ones right here. So since I made the recording with this call stack option enabled, when you select one of these markers, you can see the full call stack. And while the memory profiler, the Unity profiler will only show you that these allocations happen inside the update method of the raise stats player class, we can see that actually this called the update stats method, which instead called the format raise type method in the raise UI in a completely different class. So you might have spent a lot of time analyzing what can be grown in the raise stats player, and actually the allocation happened in other methods. In this case, we can see that eventually we call to string format to probably update some timer somewhere in this game. So this is very powerful to detect allocations and try to prevent them with other techniques, string builders and any kind of non-allocating version of things. Another common issue is asset duplication. Essentially, this happens under different circumstances, but this means that you might have the same asset loaded multiple times into memory. One common case for this to happen is when you have non-addressable assets being used in addressable assets. In this example, we have bundle 1 and bundle 2 using prefab 1 and prefab 2. Both of them needs texture 1 for rendering the prefab. But given texture 1 is not addressable, these bundles don't know where to pull the texture, so instead they copy the entire texture in each bundle. So if you load bundle 1, it will have its copy of texture 1, and if you load bundle 2, you will have another copy of texture 1. So this can be easily solved by making texture 1 addressable in a way that the bundle 1 and bundle 2 can get the same textures from bundle 3. This can also happen under other circumstances. Usually, as an example, assets repeat in both the player and asset bundles. So as an example, if you have a scene in your player, in the player build settings, that is referencing a prefab that at the end is referencing texture 1, given this scene is not addressable, it needs to be included and all its dependencies into the player content, into the APK, IPA, or your executable files and folders. And if this texture is also addressable, we need to copy it also in addressables. Even if the texture is in addressables, the player won't never go automatically to addressables or asset bundles to load it. It's your responsibility. The bundle might not be even there. So the player doesn't know anything about the content in addressables. That's why it needs its own copy. And another way this can manifest is if texture 1 is in the resources folder, because everything in the resources folder will be copied regardless of it being referenced or not into the player content. So addressable assets in the resources folder is a big no-no. So how you can detect asset duplication? We have several tools to detect this. As an example, the addressables package comes with the addressables analyzer window, which is slowly being superseded by the build report, a new feature in addressables that after each build provides a report of all the bundles generated, the content of the bundles, why one bundle references other, which asset references which other asset in which other bundles. It's very powerful. And one of these features is detecting duplicates. If you don't have the report and you have the development build, you can use the memory profiler that has a show potential duplicates tool that if you check it, it will look for all assets named the same, of the same type, weighting the same. So that's why it's potential duplicates. You might have two assets called the same, but might be actually different contents. But you can get an idea if you have duplications with this. And sometimes, if you don't even have a development build, but you have access to the bundles, you can also instead use the Unity data tools. This is a command line, a CLI command tool. It's in its own GitHub repository, which you can access right now, which essentially you analyzes a folder that contains bundles and generates a SQL database that you can explore to see which assets are in the bundles and explore some important information. So let me show you a little bit this tool. So in this case, I analyzed a group of bundles, and this SQL database has lots of tables and views that allows you to see stuff like all the animations included, all the audio included, all the mesh, shaders, and so on. But it has also the interesting part here, which is the view potential duplicates. It works similarly to the memory profiler version. It looks for assets called the same, of the same type, weighting the same. So in this example, you can see how we have two instances of the speed-a less slan texture 2D in the personal, season, and default bundles. So essentially, this is saying that we have two font atlases because the SDF kind of give it away in those bundles, and you can use the build report and so on to keep deep in dive into that. I really recommend this tool also to see stuff like texture formats and if you are compressing or not compressing textures. But again, kind of outside of the scope of today's session. And finally, regarding memory, I want to talk about shader memory. We talk about shader variants and that you can have hundreds of them. One thing to consider is that whenever you load a shader, like you are referencing it in a scene or something like that, we load all the shader variants into memory for them to be compiled when the CPU needs so. So the data is ready in the RAM for fast compilation. As soon as the CPU compiles it, because you needed it, it's moved to CPU and evict from RAM. But still can occupy quite a bit of memory if you didn't strip the shaders. So you might have thousands of shaders in memory and just using a couple of them, even if you won't compile them. Especially if you don't compile them, actually. So one way to deal with this is using the shader dynamic loading feature. That essentially is this shader variant loading settings that you can find in the player settings. It allows you to define a maximum size that you will spend on the shader variance size. But consider that if you make it small enough, you might end up needing to read in shaders from disk, which will make the compilation process slower. So a better approach will be to mix this with shader variant stripping. You can essentially tell Unity to skip from including certain shader variants into your player. You can do that with the iPreprocess shaders API, which essentially is a callback that whenever a shader is compiled, you can say return false and skip the shader or something like that. You can combine this with the shader variant collection we use when compiling or pre-warming shaders, because those are the shaders you actually need. So you might do something like skip any shader that is not referenced in the shader variant collection. So let's wrap up. We saw different things. We saw that using native profilers from CPU, GPU, and memory profilers is key if you really, really want to get into the bottom of your performance issues. We talk about that the shader's performance is not only about the GPU side of things, but also you can have pre-warming and stripping and memory issues when using shaders. We discussed that we have several Unity batching mechanisms, and using them properly, you will reduce batching quite a lot. We talk about untracked memory and this thing about everybody's scared about untracked memory, but most of the time it's not resident. And in any other case, you can use nice memory profiler tools to go deeper. Essentially, pay attention to transparent rendering and asset duplication. Are some very easy things to fix and might save you a lot of performance. So thank you, everybody, for being here. I hope you enjoyed the session.